Free axis denoted by DE Deborah, MA Mach, RE Reynolds, Deborah Mach Reynolds. These three names, Deborah, Mach, Reynolds, are dimensionless characteristics with the values starting from 0, this is the origin of our coordinate system, to infinity. Value of a Deborah number tells us something about the solid or fluid, and the difference between the solid and fluid materials are from the point of view of memory of material to the previous history of deformation or configuration of molecules, memory, history of deformation. Mach number is the second axis, enables us to distinguish between the incompressible or compressible materials. And value is speed, velocity of the motion of the moving fluid particle, for example. Therefore, velocity scale and related to the reference velocity, and this is the speed of sound. The third variable, Reynolds number, concerns the classification of the fluid flow to laminar and turbulent. Laminar means a smooth, fully stabilized and unique flow field, while turbulent flow is characterized by chaos. The three criteria are defined in the following way. DE value is a ratio of a memory time of a material, which will be called relaxation time, lambda relaxation time in seconds, characterizing a long of memory of material related to some characteristic time of a process time, or time of observation, residence time distribution and flow, and so on. Mach number, MA, is a ratio of the actual velocity of a fluid particle or material particle related to c, and c is a speed of sound. The third criterion, Reynolds, is defined as a ratio of velocity, the same velocity as in Mach, multiplied by some characteristic dimension, diameter of pipe, for example, divided by viscosity. dE number at origin is so origin is always 0. So the Deborah value starts from the origin from 0 to infinity. 0 is the fluid. Deborah is fluid. Going to infinity corresponds to the solid materials. MA, Mach number at origin is incompressible. Mach is 0 and goes to infinity for compressible materials, and also Reynolds. Laminar flow corresponds to the origin of a coordinate system 0 and goes to infinity in a turbulent. Well, the first axis is Deborah, dE, defined as a ratio relaxation time of material divided by the observation time, or time of a process. D is the name is according to Deborah. She was a prophetess or lady predicting future in ancient Greece, and she is known by the statement like this: even the mountains or rocks are moving in front of the eyes of God. What is the meaning of this statement? It's very simple. Everything is floating. Even the mountains, even the rocks, everything is flowing, but it depends upon the scale, upon the relative relationship between the memory of a material with respect to the observation time. The memory concerns the deformation. So, deformation and the rate of deformation. Let's consider a body of material at some time t prime, and let's assume that the same body is deformed due to action of forces and so on, and the time, of course, at the time t. And now, deformation is related to the changes of material fibers. Material fiber in a this initial in a time t prime is characterized by vector d, very infinitely short fiber of material, dx prime. It's a vector, therefore I am using an arrow. And this is the material fiber at the time t prime, at that time t, maybe a current time. The material fiber is extended, change its length, magnitude is changed, and also orientation. And this is a new vector dx without prime. And deformation is in fact the ratio or relationship between the two vectors. And in solid mechanics, the deformation gradient is defined as a, and f is symbol f is used for this gradient, and this is the dx over dx prime. More correctly, it should be partial derivative of x with respect to the partial derivative x prime. But what is substantial? It is still the same material fiber, only in a time t prime and time t. In a component notation, Fij is a dxj over dxi prime. Deformation gradient. This is a asymmetric tensor, and for the generation of constitutive equations, it is necessary to evaluate the symmetric part of asymmetric deformation gradient tensor, and this is the finger tensor. Finger tensor. Oh, usually the symbol B is used for this tensor of a second order, and this is simply calculated as a dot product between the deformation gradient tensor and the transpose. Of course, in index notation, tensor finger tensor Bij is a Fik multiplied by Fkj. K is a represents the dot. Here this is the dummy index. And now, knowing deformation, it is possible to evaluate the dynamic response of material, therefore stress. Stress is the simplest form in solid mechanics, 2 times G times finger tensor minus unit tensor. And this constitutive equation is called Hooke's or Neo-Hooke's form, but the meaning is the same. And you see, this is the linear relationship between the symmetric tensor of internal stresses and the symmetric tensor of rate of deformation. Of course, it is necessary to subtract the unit tensor because at undeformed state, and in undeformed state, the deformation gradient is 1. And also finger tensor is 1, therefore it is necessary the unit tensor to subtract. G is elasticity or shear modulus. I hope that you remember this terminology, these terms from the structural mechanics. So, and now, how is it in fluid mechanics? Instead of deformation gradient, there is a velocity gradient. Velocity gradient, the symbol number U is usually used, and therefore again this tensor is a d over dxi uj. Again, this is the asymmetric tensor, and symmetric tensor of associated with the velocity gradient is a rate of deformation. Rate of deformation, we use the symbol delta, tensor of a second order, and this is a 1/2 of a gradient of velocity plus transposed gradient of velocity. So this is the equivalent, this is the analogy of a finger tensor, and the analogy of a Hooke's law is a Newton's law. That's almost the same as the Hooke's law. Tau is 2 times, instead of shear modulus, there is a shear viscosity or dynamic viscosity, mu multiplied by rate of deformation. And that perfect fluids and elastic solids are extreme cases of materials. In reality, the materials are something between, and these are viscoelastic materials, characterized by non-zero de Dvorak number. Well, example, if you open doors of your refrigerator, you will find out materials like eggs, butter, yogurt, and so on. Also, viscoelastic materials are polymers, either in form of melts or solutions. Well, I'm working for 40 years almost on the attempt to describe the mechanical property of collagen as a biopolymer. Well, the constitutive equation suitable for description of a kinematic relationship between stresses and deformation is a Maxwell model, which is represented in a 1D case, or extreme simplification, as a combination of spring and dashboard. Spring is a characteristic of elastic part of the Maxwell model, therefore some modulus of elasticity, while the dashboard represents the viscous part of the model. This serial connection of a spring and dashboard is loaded by force, tau, and the response is in fact the deformation, for example, gamma, or something like this. Mathematically, this 1D model can be represented by the relaxation factor times d tau over dt, time derivative of stress, plus tau is 2 times mu times gamma dot, or pardon, forgot it. So this is 1D case. The problem, and you see that this 1D case reduces to the Hooke's law for solids and Newton's law for fluids. But it seems natural to reformulate the Maxwell, this form, to the general form with the tensors, lambda, relaxation factor, this is a scalar, this time of memory, capability of material to remember sometime the previous configuration multiplied by time derivative of. Now, tensor of stress, Cauchy stress, plus the Cauchy stress. This is 2 times mu times tensor of rate of deformation. And you see that really for the fluids characterized by relaxation time 0, it is this model reduces to the Newton's law, while for solids this first term on the left side prevails, the tau. So in this case the time derivative of stress is 2 times mu over lambda relaxation time, and times the rate of deformation. But rate, this is the time derivative of deformation. Deformation, we know, is finger tensor. So this is the time derivative of a finger tensor. And this equation can be integrated over time, also integrated over time, giving as a result a relationship that tau for solids, right? Tau is 2 times mu over lambda, can be considered as some effective shear modulus times finger tensor plus some constant, well, maybe c times unit tensor. It seems that it fits the previous analysis because this is the Hooke's law or neo-Hooke law. But so that it seems that this constitutive equation is a good description of viscoelastic materials, even for the three-dimensional case, characterized by, in fact, only two constant: relaxation time and viscosity. Okay, but there is time derivatives of observed quantities of scalar vectors and also tensors should reflect the requirement of frame indifference. What does it mean? The description of a process, experiment, should be independent. Please distinguish time derivatives. Time derivative with a partial delta means time changes at a fixed point in space, at a fixed point x, y, z in the space. Unlike material derivative, which corresponds to the moving coordinate system. Moving coordinate. The material derivative is defined for scalars and for vectors in a similar way. For example, material derivative of velocity is acceleration. acceleration of a particle. Of fluid particle. And the third kind of time derivative, which is applied to the tensors, is defined as a material derivative of the tensor plus spin tensor, scalar dot product with a tau minus tau dot spin product. And this is so-called Jaumann or corrotational derivatives. And the application is as follows. If you have, for example, a river with water flowing, and maybe that you are sitting on a bank, and maybe that you are fishing and measuring temperature of water by a thermometer. In this case, you are fixed, you are sitting on the bank, and therefore the thermometer records not the time changes of temperature of a particular fluid particle. No, it simply records the time changes of a temperature at a fixed x, y, z points. On the other hand, if you are not on the bank, but if you are on a boat, and maybe that you will be measuring the temperatures by thermometer and also by anemometer velocity u. Well, again, both is possible. But now you are sitting in a boat. Moving with the velocity u in the river. So, and this is the case of material derivative. Observer is sitting on a back of a fluid particle and is moving with the velocity of particle u. And the third case concerns again the experimenter measuring, for example, the Maxwell system, and now this observer is located on a boat again, which is not only moving along the bank with the velocity u, but which is also rotating in a vortex with a spin omega. So, taken together, there are a lot of analogies and similarities between the solid mechanics and fluid mechanics. In solid mechanics, we distinguish between the reference unloaded state of a body, which is related by a deformation tensors to the current state. But in solid mechanics, the time plays absolutely no role. So, and this is probably the most important difference, which is manifested also in units. For example, gradient of velocity has a unit reciprocal second, while finger tensor is dimensionless. Okay, the different point of view is also can be seen in character of peoples which are involved or working in the field of solid mechanics and fluid mechanics. Peoples working in structural mechanics, solid mechanics, are usually solid, conservative, and if you hear that someone is speaking about finger tensors and first Piola Kirchhoff stresses, well, and for example, Euler Lagrange equations of the first kind and the second kind. You know for sure. So this is the guy working in the solid mechanics.